In this video, I'm going to go over the preliminary passive house review report more in detail so I can explain better what kind of metrics we're looking for and what kind of output and deliverables you would get if you decide to do this kind of analysis on your project. So I just opened the zip file, and as you see, it contains 5 files. One is the main report, which we're going to cover in this video. And then the other 4 are actually 2 by 2. There's an Appendix C that addresses windows and doors, as well as the specific specs for the windows and door. And then an Appendix D that talks about the fresh air system, ERVs or HRV, as well as the associated specs. We're going to cover that in follow-up videos, so that this video does not end up being super long. This is the main report. It's done on my own house, so you're gonna see some things about my own project. In the overview and table of content, you see the full breakdown. So it's a pretty thorough report. Because of that, whenever we are done with the analysis and whenever we issue the report for a project, then we always have a live call with the client and the design team, typically the architect and the builder, to go over this report together so that we can use the report as a way to go over the goals that the project has and see what the results of the report mean for the next steps of the project. So beginning from the end, this is a table that basically summarizes some of the variables that we model for my own project and lists the results in terms of energy efficiency. This table we're going to come back to a couple of times, including at the conclusions. So I don't want to spend too much time on it. But as you see, if you can see my cursor, it talks about the combined site energy for heating and cooling. So this table is very important in order to identify where the sweet spot is for the building in terms of year-round performance combining heating and cooling. Now it is site energy, meaning that there is an assumption of some heating system and some cooling system that are listed down here with some assumed seasonal coefficient of performance of how this air source heat pump that was decided for this report performs in that location on a yearly basis. And you see, the numbers here at the bottom, 19,440 are kilowatt hours per year for the baseline for heating and cooling combined. The baseline is something that we decide on a project-specific basis, but it's typically a code minimum built building, meaning that the R values that we pick for the building are minimum compliance. In this case, we stuck to the 2021 International Energy Conservation Code, 2021 IECC. So the baseline has minimum values for insulation. For the windows and doors, we stuck with the same 2021 IECC. So this is a building, and same goes with the air leakage. And ACH3, the air changes per hour at 50 Pascal of 3, is the maximum allowed air leakage for the 2021 Energy Code. So each individual square of this table shows one scenario combining different R values, different quality of windows and doors that we made recommendations based on the climate location that the project is at, as well as the third variable is the building air tightness for this specific project. Now, these variables we're going to come back to later, but it is something that we make recommendations for each individual project. So we tailor this analysis depending on the climate as well as the specificity of that specific project. And in this case, this project being a remodel and partial addition, looking at air tightness was very important because we're working with an existing structure. Then I'm in climate zone 7, so very, very cold, we're going to see how the thermal quality of windows and doors really impacts thermal comfort. There's a specific section about that in the report, so we're going to come look at that today. And then the last variable that we looked at is the basically the amount of insulation to include in the exterior in the exterior assemblies, including walls, floor, and ceiling. So as I said, each individual square of this is a combination of these variables, starting from the code, starting from the R values, windows and doors, as well as air tightness. And so the first square you see here, the top left, has an absolute energy consumption for heating and cooling of 19,440 kilowatt hour a year site energy. So this is what the meter would read based on the assumption of the air source heat pump. Whether or not the air source heat pump makes sense in this climate is not really the matter of this study. It's just a way to compare these numbers in a way that makes sense. Now, for each of these different scenarios, for example, the two that we end up recommending here that are highlighted, we have an ACH 50 of 3.6, of 2.6, basically under this column here. Then, because of comfort, we end up speccing Passive House A-grade windows because it's a very, very cold climate, and the thermal quality of your windows and doors drives the perception of comfort. So that is what drove the selection of this column here. And then the amount of insulation we're going to see later why we're recommending medium or high R values in order, my personal intention is to certify the building as Passive House. So I want to get to those numbers. And so that's why I ended up recommending to myself to have this. Now, we do this kind of analysis very, very often, also on projects that don't have the explicit intention to certify, but they want to use the Passive House science in order to improve the thermal comfort and indoor quality inside the building. So we would do this kind of analysis for many, many projects that don't necessarily want to be certified. Now, for each of these squares, you see a number and a percentage. So 19,440 is the total amount of energy that the building uses on a yearly basis for heating and cooling. And so for this down here on the right hand side, 1,270 is again kilowatt hour per year. So from 19,000 to 1,270, it's a dramatic improvement. It corresponds to a 93.5% reduction. So the percentage over in with the blue background is a percentage of reduction compared to the baseline. Baseline will be doing a code minimum build using the 2021 IECC code. Now we're going to come back to this again. I just wanted to give an overview of how that table means. Here you have some literature that you can go over. You can download this report as PDF. There are some live links that I recommend you looking at. There's a free video here that you can look about Passive House. This takes you to the Passive House Institute website where you can learn more about Passive House, but this is more generic information that we don't want to spend too much time on it necessarily. We do this report based on a full PHPP energy modeling, Passive House planning package. And that is a software that is validated according to an ISO standard, that is an international standard for energy efficiency calculations, as well as the ASHRAE standard 140, that is a protocol to validate softwares for calculating heating and cooling loads. There's more information if you follow these links. Again, if you download the PDF. Reasons to build airtight, reason to avoid mold and condensation. Building to code minimum does not prevent buildings from having mold and condensation. So, whenever you're looking at what's the premium or why building to Passive House, there's a significant amount of value past just energy efficiency. Thermal comfort, we have a whole section later in this report talking about thermal comfort, so I don't want to spend too much time on this page, but again, feel free to download the PDF and read through it. data from monitor passive homes or passive house buildings show that the combination of an airtight building envelope and continuous filtered fresh air protects building occupants from exterior pollutants. There is some links here to the study carried out in Australia. And if you have a building that is so detached thermally from the exterior, then it will remain much more comfortable both in the summertime as well as wintertime if the power goes out. So it is a building that is much more resilient compared to a code minimum built building. Now, looking at the actual project now, on the left hand side here we have a photo of my house. I'm at significant elevation, about 8,800 feet of elevation in the Rocky Mountains in Grand County, Colorado. Beautiful view facing south, but definitely significant potential for improvement because it's a 1976 cabin that has single pane windows, very poor insulation, very leaky. So a lot of opportunity for improvement here. The plan is to do a full remodel and to add a full story to this. So with regards to benchmarking this project against passive house and NFIT or low energy building standard, which I'm going to flip back through here just quickly, we always benchmark the project against the full passive house standard. And then depending on the nature of the project, if it is a new construction, we benchmark that against the low energy building standard. That is a building standard issued by the same Passive House Institute, but with the same quality assurance and the same comfort and indoor quality, but with more lenient goals as far as overall energy efficiency. Whereas the NFIT standard is a standard that is specifically designed for building retrofits. And again, that is something that is designed with the same quality assurance, comfort, and indoor quality in mind, but the goals and the targets are more lenient compared to the full passive house. And this is the table that summarizes those differences. Now back to my project. It is a partial remodel, but because I'm adding a full story and I'm basically doing a gut remodel, I decided to benchmark this against the low energy building standard. I don't really care because I want to get to the full passive house standard. For what we do, I don't actually have an option. I'm just kidding. I just value the quality of passive house. So I want to get to the full passive house certification, even if it is a relatively small building in a very cold climate. Looking at terrain, I'm on a ridge facing almost due south. I'm just 6 degrees off from due south. It's a pretty cold climate. You see 8,760 feet of elevation, very cold climate for ASHRAE. I do agree with that statement. And in terms of significant temperatures, you see the exterior temperature for PHI comfort criterion, negative 13 degrees Fahrenheit. Now, when we look at the comfort criterion and for the selection of windows and doors, we're going to come back to that negative 13 because that is the temperature that we use in determining the comfort conditions inside the building and what that's what's going to drive our decision in selecting windows and doors. Now, side terrain, you see the contour lines. It's a beautiful site, has a ton of sunlight. The only shading elements surrounding are literally just trees. Most of them are aspen, so they lose their leaves in the wintertime. So there's a lot of sun, and we can take a lot of benefit from that in terms of passive solar gains. We're going to see that in this report later. It's a very simple shape. That's one of the reasons why I bought this property, because it's a very compact shape, and it lends itself well to be worked with. Then we're gonna skip that. This is a little bit of the solar axis and shading. You see orange and lighter orange. Let me zoom in closer here. You see a lot of solar access on the south and east just because of the orientation of the building. And the window to wall ratio, this is a building that I designed myself. My background is in architecture, so it was fun to go back to the drawing table and experiment with that. But the building itself is really taking advantage of the view being to the south. So while the climate is very cold, the solar axis and the views overlap significantly. Um, on the other hand, on the right hand side here, you see the distribution of shading, and there's some shading on the north side because of some trees, but that is really insignificant for our purposes. So this is something that the report provides us with information as far as giving a big picture or quantifying how much access we have or how much shading we have, because sometimes we may have a perception that is not really what the building sees as far as shading and solar access. This is the full 3D model from of the building. You see that we have aspen on the south mostly, which have deciduous leaves, so it's very convenient because in the wintertime they shed the leaves and it's a pretty unobstructed view. Whereas the evergreen vegetation on the west and north is pine trees. But in the first place, they're not very big. This used to be a sawmill property, so all the trees around here, they're not very old. I'm guessing the oldest tree around here is about 30 years old. But they're also on the west and on the north side, so it doesn't really impact the access to sunlight and passive solar gains. Identifying the building envelope is a crucial part of making the project efficient. In this case, it was very easy because I started designing this with the clear goal of having passive house as a goal. Again, you don't have to have the goal of passive house certification to do the report. It's something that you can benefit significantly even if you don't shoot for passive house. In this case, this is showing, right now the building only has one story, that is what is shown here in orange. The mudroom and garage are going to be added and they're going to be unconditioned. In the section view, this is what it looks like. The current structure is just this story where my cursor is. I'm going to add a full story, the mudroom and the garage space. The current structure is on piers, which I'm going to enclose in a form of a unconditioned crawl space, mostly to protect the plumbing and prevent animals from getting under the house. Some key parameters here: it's a fairly small building, 1,500 square feet, with including the addition, not including the mudroom and the garage. About 5,000 square feet of skin, skin being the assemblies of the building envelope, so exterior floor, walls, roof, all the exterior doors and windows, sum up to about 5,000 square feet, and the form factor is about 3.2. Now 3.2, granted how compact the building is not great, but it's a small building, so really this is something that you cannot really fight geometry against. And that is, we always look at the form factor when we look at recommendations to give to specific project, because if the form factor is not favorable, then it becomes a lot harder to achieve any improvement in the energy efficiency of the building. Thermal mass is something that is in general overrated for residential buildings. In this PDF, I included a link to a study done by PHI showing that. I am considering using a double drywall board on the interior walls to have some more thermal mass and thermal capacity. But given the existing condition and the fact that I'm working with existing foundations, I don't really have the option of adding significant amount of thermal mass, such as a slab over the floor or something like that, because it would be a very big risk or pain in the butt for the structure point of view. So whenever we do this kind of recommendation, we try to keep in mind looking at the building holistically. Again, our background is in architecture. We are not energy engineers. We try to look at the priority of the whole building before we make recommendations about the energy and the envelope in one way or another. These are the variables that we selected for the project. Me. And we make these recommendations on a project-specific basis after we have an initial call with the client. So in that initial interview, that's something we do. We don't charge for that. We just try to see if this could be a good fit for your project and see how we can help you with. And we try to see what your goals are, what the main constraints to the project are, as well as what the climate is like and what the design is like. And we typically select variables that are going to be impactful for both the performance and the budget. Be impactful for the budget means, oh, I'm looking at this expensive window package. Is it really worth it? Is it overkill, or is that something that I actually need because my climate is very severe and I need more thermal protection? So we have part of the PPHR process, preliminary passive house review process. You reach out to us and typically send us a drawing set for us to have a look at. And based on the drawing set, we would have an interview call basically where we chat. It's a typically about 30 minutes to an hour, not really longer than an hour, but it's just a conversation to try to understand what your goals are and go over what we can do to improve your project. So these variables is something we come up with based on that conversation. Moving forward, something that I wanted to reiterate is that for this project, for every project we have a baseline. A baseline is something that, looking at for example, the first variable, the R value targeted means selecting how much to insulate the exterior walls, for example, starting from a code minimum and then increasing on that and seeing how much of a difference it makes. The second variable is, in this case, windows and doors, the thermal quality of windows and doors. So basically, the heat losses and how getting better performing windows, starting again from a code minimum window and door package. And the third one was, in this case, was specific because in this case it's partially remodel, so getting a very good air seal on the existing part of the building is going to be not impossible but challenging. So looking at that, how much that impacts the performance of the building is going to be significant. So the baseline of this report, which is something that is very important to keep in mind, we always need a baseline. In this case, is having code minimum R values. Code minimum is the 2021 energy code. That is something that a lot of municipalities have not yet adopted, but it is something that we try to refer to the latest energy code. Then code minimum windows and doors, we're going to see how bad those are for thermal comfort. And then looking at code minimum air sealing the building to barely meet the latest energy code, and then increasing that air seal to make it more comfortable as well as more energy efficiency. So that is the code, the project baseline. Looking at the R values, how much that matters. So we intentionally do not model a specific wall assembly or a specific roof assembly, even in cases like this where we have an existing structure. The reason we do that is because at this stage, and one of the primary purposes of the report is to feed information during the feasibility study. And at this stage, we don't want to funnel and lock the project into a type of wall assembly or a specific product that then, if we change that specific product, then we have to go back and change the modeling. So we use standard R values that are listed here, starting from the code minimum R26 volt, so this would be the equivalent of the 20 plus 5 in the actual energy code. But we basically do that so that we can keep doors open down the line in making decisions. Again, our background is we are architects as a background, so we are very familiar with the different steps of the project and how going from a schematic design to design development, the project evolves and things are decided. So this is, in our opinion, the best way to address the selection of the R values and see how much that of an impact it makes. Then we spent a lot of time talking about windows, doors, skylights, and other glaze components. As I mentioned, we have an appendix, Appendix C, and a whole Emu specs spec sheet, spec 2, that are dedicated to the Windows doors and similar components. So we're gonna come back to those in a shorter video after this one. And we do that, we look at windows in such detail because good windows are crucial to achieve thermal comfort, to keep water out. They can be very expensive and they impact the aesthetics as well as the functionality of the design. So windows, doors, and transparent components in general are very crucial in getting a good quality building. So we have put a lot of language here to explain the why. These are the quality of the frame that we looked at. So I recommend you taking a look at all these documents attached. A good quality window is not just a triple pane window. We have a whole course describing that, and once you switch to triple pane, then your frame becomes the weak point. And so we look at the specific quality of the frame, thermal quality of the frame, so that you can make a decision that is consistent with your thermal needs in terms of thermal comfort, as well as what you can afford in terms of feasibility, and what fits in the aesthetics and the design of your project. In this case, we looked at just two types of glass. Because of the elevation and because of the climate, we want, in our experience, we want to have high gains glass. This is where we could have modeled dozens of types of glass. And because we do this kind of modeling, like 1 or 2 new building a week, so we can come to the table and cut through a lot of the unnecessary modeling and say, okay, really we want to look at these 2 types of glass because in our experience, this is what makes a difference. We do report both the European values, performance values, as well as the national North American values, because if you're shopping around and if you're looking at American manufacturers as opposed to European manufacturers, they use different metrics. And so the same glass would perform differently depending on how the Americans model it or depending on how the European model it. So we provide both, so you know what to look for, whether you're going with a European one or an American one, or if you want to compare apples to apples. That is very important so that you can understand what you're buying. Looking at doors, something that blows people's mind is that a door to an unconditioned garage belongs to the building thermal envelope. A hatch to an unconditioned crawl space or to an unconditioned attic is part of that thermal boundary, so that needs to be insulated, that needs to be airtight. So we provide values for those as well as part of the preliminary report. Details about avoiding condensation and achieving comfort. There's a specific appendix going over this, so we can cover that later. This is probably one of the most important tables of the whole report. I want to spend a minute on this because why do we do this? Buildings. We want to have comfort. We want to have better conditions than living outside. That is why we do buildings. It's philosophical, but it is important to understand the why, or to keep in mind the why, because otherwise you just forget why we're doing buildings. And you'll be shocked to see, you're going to see that in just a second, how poorly performing code minimum windows, windows that barely windows and doors that don't have any other uh, performance aspirations than just complying with code. And that is represented in the first column here. We've modeled the entire building using windows and doors that do comply with the 2021 Energy Code in terms of frame and glass. And from a 0.3 nominal U value or U factor, once you account for the installation D rating, from a 0.3 you end up to a 0.36 U factor. And doing the science, doing the math, in the climate of Grand County with negative 13, remember, exterior temperature ends up with an interior surface temperature of 46 degrees. That's pretty cold. Now, negative 13, or the design temperature used by the Passive House Institute to calculate thermal comfort, is the average temperature of the 12 consecutive coldest hours of the year. Meaning that in selecting the weakest links of your building envelope, you want to make sure that they're going to ensure comfort even in the coldest time of the year. And that is this temperature here, negative 13 Fahrenheit, for the climate of Tabernacle, Colorado, at my site location and elevation. Now, following the science and doing the math, the science of thermal comfort says that in order to feel comfort, or in other words, to not feel discomfort, the human body wants to have all the surfaces surrounding our body being the same. The same, so to speak, means that the maximum delta in temperature on the surfaces that the body allows before feeling uncomfortable is 7 degrees 0.6. So if the surface temperature of my window is at the delta between the window and the room, the delta is greater than 7.6 degrees, then I feel discomfort. And looking at brand new windows that only comply with energy code, the average temperature is going to be 46.2 degrees, meaning that my delta is 3 times greater than the maximum allowed. So I'm going to feel very uncomfortable. So that is why I for sure will not follow the energy code in choosing windows. Now, number 1, 2, and 3, I have switched to good triple pane. Good triple pane means a fat triple pane. That is something that it's worthwhile expanding upon. I can cover that in the next follow-up appendix video. We're talking about different types of triple pane, but a lot of American window manufacturers only have space on their frames for 1/2 inch glass, meaning that that's not enough insulation to provide extra thermal protection. This glass here is about almost 2 inches thick, meaning that I have a lot more protection and just a lot more insulation because I have a much thicker glass pockets, not the glass pane itself, but the whole glass assembly comprising of the 3 panes and the 2 glass pockets filled with air, filled with gas, argon gas, not air, and 2 low E coatings. So this is something we can cover later. But I also have 3 different types of frame, 3 different families of frame. We're going to see in the follow-up video about windows what those are. C grade, B grade, and A grade, just like in school. A is better than B, B is better than C. So these have the same type of glass, just the frame is better, and number 3 is the best. And you see that the better the window, the higher the temperature I get on the interior surface of the window, and the closer I get to that, to meeting that requirement for comfort. So this is, again, probably the most important table of the whole report with regards to thermal comfort, and also to allow you to navigate through different window products, because windows are very expensive. Good windows and doors are very expensive, but they're also very important for the comfort inside the building as well as for the aesthetics. So this table, we do this for every report that we do, and it's really the way we try to make recommendations as far as which family of performance, which grade to shoot for. In the follow-up report about windows, we're going to look in depth what is an A grade frame, what is a B grade frame, and what is a C grade frame. Again, you don't need all of this necessarily depending on your climate. This is big. I made this selection because I'm in a very cold climate, but if you're in climate zone 2 or 3, for example, you can get to passive house probably with just a double pane, and you still meet this very high thermal comfort condition. So this is something that is very important to navigate through different products because it's easy to assume that to get to passive house, all you need triple pane windows. Triple pane windows can be very poorly performing depending on the type of glass and the type of frame. And B, depending on your climate, you may not need triple pane. You may have very high comfort with just double pane. So this analysis is very important for you to be able to navigate that. This table is pretty much the same science. We just applied that science to a range of temperatures that is not just the critical temperature of the location. That critical temperature of the location is that negative 13 that is shown by this blue dashed line here. But this shows the temperature on the inside of the windows, and this also accounts for the window size in the building. So there's a little bit more to be talked about that, but we can cover that in the follow-up video. But you can see this is the window that complies with just the 2021 energy code, and all the way to about 40 degrees, the temperature on the interior surface of the window remains comfortable. Whereas as soon as I drop below 40 degrees, I fall into the thermal discomfort zone. Then these other three ones are C grade, B grade, and A grade frames with the same glass. So you see how much just the frame impacts the performance. And again, in the follow-up video, we're gonna go over some example of what an A grade window is compared to a B grade and a C grade. Now, moving towards the energy balance, the next couple of graphs illustrate the balance in wintertime between gains and losses at the windows. So this graph shows the energy balance by aspect of the building. So all the south window, or the east window, or the north window, in using low gains glass. You can turn up or down how much passive solar gains you allow through your glass into your building by choosing different types of coating. There are different types of low E coatings, and we make recommendations as far as which one to pick for your building. And we're gonna see the impact of using high gains glass versus low gains glass, both in terms of summer performance as well as in winter performance. This graph shows the winter performance, and for all glass being low gains. Now there's so much sun that even a low gains glass provides more gains than it causes losses. That is unusual. Typically when you have low gains glass, there are more losses than gains, but my site particularly has such a great access to sunlight, as we saw earlier, that even a low gains glass gets more gains than losses. And so that's why we do the full three-dimensional modeling of the terrain and the trees and the surroundings to really understand well what kind of access we have to sunlight. Now the same graph looking at medium gains, so we just changed the coating on the glass, going to a medium gains glass, this one, and this is looking at high gains glass. For this one, you see that the gains far outweigh the losses with the gains glass, with the high gains glass. Now, is that too much? We're gonna see that when we compare the winter performance against the summer performance. So we're always looking at how the building performs year round, um, because we don't want to sacrifice the gains. If we just did a project in North Carolina, Clemson 3, where their default was to go to low gains glass. We actually found out that the sweet spot was going to medium gains glass, because it would significantly reduce the need for heating in the wintertime, which they still do. Even if it is climate zone 3, they still have quite a bit of need for heating, and it will not cause too much increase in cooling. So we try to find the sweet spot for the building and see how that performs in all seasons. Looking at shading, we did some recommendation with shading because of this type of building. Because this building is such a cold climate, looking at different types of shading was not really a priority. Whereas if you're in climate zone 2 to 3, looking at interior adjustable shading versus exterior fixed shading or adjustable shading, those are options that we can model. And so those would be variables that we talk about at the initial interview. And we would make recommendation as far as whether to investigate a type of variable or not. Again, for this type of project and for this location, I do assume we're going to have interior shades for privacy and glare control. It's Colorado, so it can be very glary because it's very sunny. But I did not investigate exterior shades, for example, because the weather up here can be severe, can be very windy, can be very sunny. So anything that is on the outside of the building is going to bake in the sun and require more maintenance than something on the inside. So again, we try to have a holistic approach to the building and make recommendations that look at also the longevity and the durability of the building, not just the immediate energy efficiency goals. Shading, this is what the software looks like. At the top we have winter shading, so the aspen have lost their trees, and you cannot really see too well, but there are sail shades that have been removed here. This is where the deck is going to be. Whereas at the bottom you see this is the summertime at the bottom, and you see the aspen have the leaves as well as the sail shade is covered in the deck. And this is represented in the shading mask here on the right hand side. So the shading mask is something that the software calculates for each individual glazed door and window. This one particularly refers to this blue window here behind the post and corresponding to this one down here. You see that window and the dots here represent the apparent sun path in the sky in the winter time, that is at the bottom, as well as the summertime where the sun is higher. And you see without the shades, this is a fair amount of the sky, and the aspen here are just in the background, they lost their leaves. Whereas at the bottom here, you see it's much darker. This is the sail shades protecting the glass. And you see the aspens have their leaves down here, but they are too low to actually shade anything. So that's why I ended up using a sail shade, because the aspen, even in the summertime, the glass is still pretty exposed to the sun. So this is something that we will be deciding with you at the initial interview, if that's something that you want to pursue and investigate. And we're going to make recommendation as far as what is going to be impactful or not based on our experience. Fresh air, we have a whole appendix and spec sheet talking about ERVs and HRVs. Just from a qualitative point of view, this table shows the airflow rate that you would get per occupant, depending on, in two cases. One would be code minimum ventilation, so just your regular conventional bathroom fans on a 24-hour basis, on the assumption that you go to the bathroom so many times and you turn on the fan for however minutes every time. So this is based on the expected occupancy of the building. And you see a person should get in average about 18 CFM, cubic feet per minute. And so 12 is definitely not good enough. And keep in mind that this kind of ventilation has no filtration. So any pollution that is present on the outside would come in. In my case, it's so dry, it can be very dusty outside. And when it is pollen season, both the aspen and the pine release a lot of pollen. So if you're allergic, that can be hell. If you're in the city, you can get a lot of pollution coming in, or if there is a lot of wildfire smoke outside, or whatever type of pollution, you have no way to filter it out before that pollution comes in. So looking at the second row here, looking at the design rate that we have specs for this project, we're gonna see in the follow-up video about the ERV, we get above that 18 CFM per person. So we do have design for indoor air quality. That is the main purpose of the ERV or HRV. Yes, the acronym means heat recovery ventilation or enthalpic heat recovery ventilation. But the real purpose is to have high indoor air quality. We get that by granting a certain amount of fresh air per participant and filtering out pollution. So this system comes with an F7 filter on the intake that blocks off a lot of the pollution, whether that is pollen, dust, or just pollution from the city. Heating and cooling, this is something that we use in talking with the HVAC contractor. And as part of the report, we provide heating and cooling loads for the whole building so that we can talk with the MEP engineer or the HVAC contractor with regards to what kind of heating and cooling system to have. So these two tables show the heating and cooling loads for each of these scenarios that we model. This is the same squares that we saw at the beginning, starting from a baseline of code minimum construction. So looking at code minimum, let me zoom in closer. Looking at code minimum R values, code minimum windows, and ACH3, ACH50 equals 3, we will have 49 kBtu per hour heating load for the whole building. In the scenarios I end up recommending for myself, I end up having about 10, so reducing the heating load by 80%. So even in terms of what kind of heating system I will need, I am going to need a dramatically smaller mechanical system because my building is so much better to begin with. From the same point of view, we provide cooling loads. Again, this is something that would be used for the sizing of the cooling system. Again, a kilobtu per hour. I end up with 7, meaning that one head of a mini split would cover for the entire building. Again, this is something that we provide for each report, and it's something that can lead to dramatic savings in terms of mechanical systems, and it can be used to size up your heating cooling system. Now, getting to the energy performance. This is where we start looking how the building performs in the winter time in this page, and the next page is the winter time. And I'm going to zoom in closer because this is very cool, but also very important to understand. So this is the energy balance. On the left-hand side, we have the baseline. So just looking at these two columns with my cursor is, we have the losses through the building, and we have the gains for the building. Losses are through air leaks and ventilation, the green box. Losses through the windows, the yellow box. And then we have the floor over that crawl space, the walls, and then the ceiling. On the gain side, we have the passive solar gains through the windows. So the yellow to yellow is losses through the windows and gains through the windows. In orange, we have the passive solar gains, such as people, computers, appliances, cooking, taking showers, and whatnot. So heat that is emitted inside the building by occupants. And then the huge red box is the active heating. That is what we want to tackle in order to make the building more efficient. So this is the heating demand of the building per square meter. This is the metrics. Now, for the scenario that I'm probably going to pursue, I updated, we have the same balance on the right hand side here, again, and this is, down here you see high R values, ACH 50 or 0.6, and passive house A grade windows and doors. So this, we basically have one of these for each of the little squares that we looked at for each combination of the variables that we model. We dramatically reduce the leakage and the ventilation losses, the green box. We dramatically reduce the losses to the windows and doors, as well as to the other components of the building. We have made it so that we selected better glass. So we have, the result is that from 216 kilowatt hour per square meter a year, the active heating drops to 13. This is the 95% reduction, or whatever the number is. So our building ends up being a passive house. So that is one of my specific goals. This table, these two graphs here are just an example. We're going to have a table comparing each scenario for heating by itself and cooling by itself, and then heating and cooling combined together to find the sweet spot of how the building performs best throughout the year. So the purpose of this table is to show you the dramatic drop in active heating from a baseline of bringing the building, the existing building and the addition to comply with the 2021 energy code, that is this table on the left, compared to complying with the actual passive house. So we have a dramatic drop in need for heating, meaning that the building is dramatically more efficient. Something that is also very interesting is that passive house is not passive solar. Passive solar is an old movement that was looking at basically experimental and empirical guesses on how to make the buildings more efficient. Passive house has a lot more science behind it, a lot more energy modeling, but there is some heritage of passive solar in passive house, especially when it comes to heating dominated climates such as this one. In the passive house scenario here on the right hand side, you see the losses to the windows here on the left, and the passive solar gains to the windows here on the right hand side. And you see that once we do the magic, so to speak, and we do all the tweaks to improve the building and improve the window package, then the passive solar gains through the windows are greater than the losses to the windows, meaning that the windows and doors, any glazed components, provides the building with more energy than it causes losses. So, and the ratio of one unit of loss to 2 units of gains is a very sweet spot for passive house buildings in heating dominated climates. It's not something that you pursue in passive house buildings in hot climates, of course, but in cold climate, that is definitely a ratio that is very effective when you start seeing a 1 to 2 ratio. What about cooling? This is cooling. We do the same for each scenario. We look at how the building performs year round, and basically cooling works slightly differently. Long story short, you see how all the dynamics drop down. You do have a tiny bit more cooling than the baseline, but the active cooling is the little tiny blue sliver down here where my cursor is. So compared to the huge red box for the active heating, in this case, it is dramatically better to focus on the winter performance of the building for this project specifically and for this location specifically than on the summer performance. And this is something that we try to balance out depending on the location of the building as well as the design of the building. Now, looking at the heating and cooling by themselves, This page is kind of misleading. If you look at the report, I don't want to dive into this number too much. You see that by means of our default color coding, these boxes here look very scary because the cooling goes up by 400 times or more, but the 400 times compared to a baseline that is a tiny little mouse. Whereas you are in the same scenario, you're removing 95% of heating compared to a very big baseline that is an elephant. So this page is a bit confusing. And the way to look at this is looking at the heating and cooling combined. This is the same table that we saw at the very beginning of the summary. This is the same table that we're also going to come back to at the conclusion. So I don't want to spend too much time on it. Just wanted to point out that this is the table you want to look at because it shows the combination of heating and cooling together. The reason why we look at the site energy is because you cannot really add the net demand that we saw on the previous page between heating and cooling. You need to have some assumption as far as the heating and cooling system, and this is why we look at the site energy. But anyway, so this shows the combination of the two heating and cooling combined together. We're going to come back to this table at the conclusion, so I don't want to spend more time on this. Now, benchmarking against the full passive house standard, the target heat and demand, so you can internationally, you can call a building a passive house if your heating demand is equal or less than 4.75 kilobtu per square foot a year. And these percentages here tell us how much higher or lower we are compared to this benchmark. And if it is orange, it means that we are way high. If it is blue, it means that we are lower. So we are trying to look at a light blue or white, keeping in mind that we also want to be realistic with regards to the goals we set for our building. Now, you see at the top here the level of airtightness that we get, 3 ACH. While there's a lot of builders that complain about it, that is code minimum for the 2021 energy code. And it's actually pretty straightforward to get to. But I would consider that a deep failure on me if we only get to 3, as well as if I only got to 1 ACH. ACH is the air changes per hour that you measure at the blower door test. The tighter the building, the lower the number. And to certify as passive house, you have to be at 0.6 or less. Now, in our practice, and we're lucky to work exclusively basically in passive house, on passive house projects, and with builders that really care and very thorough and methodical about what they do, 0.6 is almost a failure, 0.4 or 0.3 is the norm. So on the other hand, I am working on a building that is fairly small, and the smaller the building, the harder it is to get to very small numbers. And part of my building is a remodel, so I don't have the best of the best options on the table. So I want to be realistic. In other words, shooting for 0.3, I'm going to shoot for 0 because why not? But also, I'm going to try to be as low as possible, but I don't want to set my target to 0.3 from a design standpoint. I want to hit 0.6 as a design standpoint, so anything that I achieve lower than that is going to be gravy on how the building performs. So I'm going to look at this table here. When we were looking at table 8 earlier, talking about comfort, we saw that the A-grade windows is the way to go in my climate because of thermal comfort. So I'm looking at 0.6 ACH 50 for passive house certification. I'm looking at A-grade windows and doors because of comfort, so I end up here. So I'm going to, this is based on this two that we made a recommendation to go for medium or high R values. So when we come back to the conclusions, we find the same table. The orange dashed line is on these two tiles. because of this consideration and the goal of I want to certify as passive house. Now, part of the passive house standard is also meeting the cooling demand, which is set at 4.75 kilobtu per square foot a year, plus some additional allowance in terms of dehumidification. So, for example, Austin, Texas could be something like 7 or 8. Florida could be like 55 because it's so humid. Where I'm at is very dry, so it remains at 4.75 kilobtu per square foot a year. Now, it's cold here. So whatever you see that in any scenario that we model, I'm always below that maximum cooling demand needed. Now, the next page is the same numbers, the same results, but benchmarked against the PHI low energy building. And the difference is that instead of 4.75 target, the target is 9.5. In other words, if passive house and the 4.75 is the full marathon, the 26.2 miles, low energy building standard is the half marathon. So instead of 26.2, it ends up 13.1. So instead of 4.75, it is twice as much the allowance, so 9.5. And you see that, hang on, let me zoom out. You see that once I move away from code minimum, and once I start to get to the correct ACH 50 for the low energy building standard, the maximum allowed air leakage is 1 ACH 50, then it's pretty straightforward to get to. So the low energy building standard is something that we often use for buildings that are either complex in form or don't have good orientation or are small. So even in my case, it will be very easy to certify as low energy building. I want to be off grid eventually, so I want to reduce my energy consumption to a minimum before I start looking at PV. So I want to go to full passive house, but the low energy building standard would be fairly straightforward to achieve. And so in our experience, in our practice, the passive house low energy building standard is always a good plan B, and it gets you to a similar performance as a fuse certified building. Fuse certified building being a building certified with the Passive House US Passive House, what they call Passive House internationally would be the low energy building standard. Now, getting to the conclusions. This is the same table we saw at the summary. We talked a lot today, so I appreciate your patience. This is the square we got to when I was looking at the passive house standard, so 0.6 ACH 50 because of certification, as well as I want to have a very tight building for durability and comfort. But I don't want to commit to 0.3 because my building is small and it's partially remodeled, so it's going to be, I don't want to be overly optimistic. So I want to keep the 0.6 as a design goal, and anything that I go above and beyond that is going to be gravy. Then the A grade windows and doors is for comfort, and I end up choosing between medium and high values, which we're going to see in a sec what that means. So at this point of the report and the review, we go over, basically this review is a conversation between us and the team members, including the client, the architect, the builder, and pretty much it's not just a monologue of me going over this. It's a lot of back and forth with questions being asked, looking at how one choice would impact the project, would impact the budget, would impact the aesthetics or the time frame, the sequencing and whatnot. Now, the next couple of pages show some additional appendixes, but first we want to see what the next steps of my project are. So as I said, getting to passive house, I need to get medium or high R values, probably gonna go with high. Need to get 0.6 or less at the blower door test, and getting the A grade windows from the A grade family because of thermal comfort. We're gonna see in the next video what that means. Then getting to the low energy building is pretty straightforward because it's going to be much easier to get to a 1 ACH 50 that is the maximum leakage allowed. And in terms of energy efficiency. It's like running the half marathon, so it's going to be much easier to get to. Not my goal, but it could be the goal for a project that cannot really get to passive house certification. So the next steps for me is going to be looking at window products and get started to price them out. We're going to see in the next video Appendix C and Emu Spec 2 that are specific about windows and doors. Then looking at typical wall assemblies, we're going to see that in this video in Appendix B, that gives us some typical wall assemblies and the thicknesses associated with that. And then looking at the mechanical system. In fact, my next item on my agenda for my project is to get back to my HVAC guy, say, hey, dude, I have the heating load for the building and I have the specs for the ERV. Let's get together and look at the mechanical system and whatnot. And with regards to this report, we're in another video as a follow-up, we're going to go over Appendix D and Emu Specs 3 because that is part of this report package that we provide as part of the preliminary passive house review. Then these are the conclusions. This is something that we would go over with the team and looking at the next steps. Appendix A is more a memo on what we consider to be part of the building envelope. So that gets back to the team. And this project is very straightforward. You have an existing building. I am going to attach a garage and a mudroom. But in some cases, some may choose to include the mudroom in the condition space or not. The garage, I would strongly recommend against you including that in the building envelope because of air sealing of the doors and then ventilation of the garage is something that is very critical. But anyway, so Appendix A is what we call the pencil rule, basically identifying the assemblies that separate the portion of the building that we condition, that we put effort towards actively heating and cooling from the portions of the building that are unconditioned or partially conditioned and from the outside. Looking at this section, I may in the future decide to partially condition the garage, especially if I have an electric vehicle or batteries. I may in the future decide to partially condition this crawl space / basement if I have any mechanicals or if I have a shop down there. So, but the orange line here identifies the main building passive house envelope. So Appendix A is just a reminder of that, and that becomes very helpful in buildings that are more complex than this one to show did we include that crawl space inside the envelope or not? Is that crawl space for us conditioned? Do we recommend it to be conditioned or not? Is that attic conditioned or not, and why? Then Appendix B looks at the R values that we looked at earlier. I'm going to flip through real quick and find the table that we refer to in Appendix B. So this page 27, but rather table 6, is the table that summarizes those R values that we use in the report for low, passive house low, medium, and high. Again, in the report, we do not model a specific, I have a 2x4 on a 2x8 plate, 16 on center, staggered, that bullshit. We don't model that because we want to provide a set of results that apply to multiple options. So in other words, we don't want to funnel the project into a specific single solution. We want to take a step back and look at the big picture. Now, in the energy model, we do account for some derating of these R values to look at the effective R values based on standard derating that we see across multiple projects. So an R60 nominal may end up being R55 or something in the energy model. But that does not matter. What matters is that to try to get to those to assemblies that are buildable, and we provide a couple of examples of that in Appendix B. So Appendix B takes the R values listed in Table 6 and translates them into a couple of assemblies for you to have a look at. So the first one is a 2x6 wall with exterior insulation, and you see some explanation there. And in this type of assembly, if you wanted to get to the medium R values, you started from the inside, you have 1/2 inch drywall, you have your 2x6, you have 1/2 inch of sheeting, and to get to those medium R values, this is for climate zone 7, so keep that in mind, you will be basically looking at 13 to 15 inches of exterior insulation. So this type of assembly, probably not the best, or you're probably going to look at some larsen trusses system for this kind of assembly. But this Appendix B gives you an order of magnitude of what you're looking at in order to get to those medium R value or high R values that we called out in the report. Now, looking at the same targets for R values, but instead of 2x6 assembly with continuous insulation, looking at a double stud, this is what we're looking at, and this is what it would look like to get to the same R values in case of a double stud. So you have your 1/2 inch drywall, you have some air gap, there's some description here as to why. And in this case, from the interior face of the interior stud to the exterior face of the exterior stud, you're looking at 15 to 17 inches more or less. Now keep in mind there are some details here as far as staggering the studs and whatnot, but this gives you some guidance of how to translate those passive house R values into something that is actionable. Now, the report does not include construction detail. That is not the scope of the passive house review. If you're interested in the passive house, in standard passive house detail that are optimized for your climate to get to passive house, you may look into the Emu's pilot program, and you have a link to that right here. So again, in the PDF, you have multiple links. If you're looking for actual construction details, you may look into the pilot program. But for every pilot program, we always require the preliminary passive house review to be done first. And the preliminary passive house review is a final piece of scope that gets you this report, and then we can have the review call together live to go over this report and decide what the next steps are for your project. That being said, I'm done with this video, and I'm going to then record the one about windows and the ERV, because those are two very important pieces that come out of this report, and they are very important for the success of your project as far as thermal comfort and indoor air quality. So I hope you have a chance to look at those as well.